Okay, so let's try exam number 1. My name is Gary Chotiner, or GSC2. Problem number 1. Betty is enrolled in Physics 121 this semester. She's anxious to earn bonus points, and starting from her aisle seat, D equals 15 meters away, rushes to the stage along a straight line. Okay, starts from rest, accelerates at a constant rate, and this is obviously a 1D system with origin x equals 0, defined in the problem, and students are at positive values of x. So we're told to start by writing Betty's equation of motion. X is a function of t. Well, in general, an equation of motion in one dimension is x at any given time equals x naught plus v naught t plus 1/2 at squared. That's on the formula sheet if you don't remember it. And for this particular case, she starts 15 meters away. D equals 15 meters, and that's in the positive direction by definition in the problem statement. V naught, she starts from rest, so that's 0. And we're told the magnitude of the acceleration is 2.0 meters per second squared. How about the sign of the acceleration? Well, she's starting 15 meters in the positive direction, heading towards 0. So that means she's gaining negative velocity as she goes. So the actual acceleration is negative 2.0 meters per second squared. Velocity is increasing but becoming more negative as time goes on. So that means I can just write x as a function of t as 15, and there's no v naught term. A half of 2 is 1, and it's a negative. So just minus 1, I won't even bother writing the 1, minus t squared. That's my answer to part A. Okay, how about part B? How long does Betty take to get to the stage? Well, let's see now. We're given the D that she starts from. She ends up at 0, so that's basically the same as her delta x, or x 1, x final minus x naught. And we're given A and V. They're known. V naught is 0. So those are known, and we're asked for the time. So now I have to think about which of the, and it's constant acceleration, so I have to think about which of the constant acceleration formula is the best one to use in this case. And as always, you have options, but some of the options are poor choices. They'll take more steps, more work. And so what my approach is going to be is I'm going to notice that the same equation of motion, x equals x naught plus v naught t plus 1/2 at squared, it's just x equals that. I know x minus x naught, I know v naught t, which is 0, I know the acceleration, so I ought to be able to solve this equation for the time. The equation again reads, and I'm copying the answer to the first one again, 0 when she reaches the stage equals 15 minus t squared. Okay, so I'm solving for the time when her final position is 0, and so t equals the square root of 15, and you can drag out your calculator, but I've already done that, and I know it's 3.9 seconds. So that's the answer to part B. Part C. What is Betty's velocity when she arrives at the stage? Okay, so I want to know her velocity at some time after she starts, but there's an equation for that, for constant acceleration. The velocity at any given time equals v naught plus at. And we know v naught, which is 0. We know the acceleration, we're given that, and we know the time when she reaches the stage. We've just solved for that. And so this one's pretty easy to apply. Her velocity at time t equals 3.9 seconds is 0, and her acceleration is minus 2.0 meters per second squared. And the time is 3.9 seconds, so this is just negative 7.8 meters per second. Done with part C. Part D. What is Betty's average speed? Okay. Now speed average, I'm going to use S instead of V. We did that in lecture. So speed is S is just equal to delta x over delta t, the final minus the initial position. It's an absolute value of that. Speed isn't negative like velocity can be. And so she moves 15 meters in 3.9 seconds. And so her average speed is 3.8 meters per second. And I don't have to worry about the negative sign in delta x. That leaves us with part E, which is to make a plot. So let me start a new page. Okay, let me drag out a straight edge. Okay. Make a plot of Betty's position as a function of time. And the problem statement suggests I start by giving the value of her position at t equals 0, 1, 2 seconds, etc. So I already have an equation for x as a function of time. X of t equals 15 minus t squared. Of course, the units I have to work out to be meters. So I can say, well, x at 0 is 15 meters. You get that from the equation or the fact that you plug in 0 for t squared. X at 1 second equals 14 meters, 15 minus 1 squared. X of 2, that's just 15 minus 4, is 11 meters. X of 3 equals 15 minus 9, or 6 meters. And x at, now I don't want to plug in 4 because she stopped by then. X of 3.9 seconds, we know, is when she reaches the stage, and that's equal to 0 meters. So now I just have to plot that. So let me just draw the line. Oop. And mark off even time. 1, 2, 3, 4. 1, 2, 3, 4. Time in seconds. On the vertical scale, 5, 10. Let me expand that a bit. Try to make nice even ones. 15. And so this is x in meters. 5, 10, 15. Plot my point. She starts at 15 meters. At 1 second at 14 meters, so down just a little bit. At 2 seconds at about 11 meters. At 3 seconds at 6 meters down here. And reaches the x equals 0 axis there. Connect them up with a smooth curve. And that's E. F. Okay, for F, I want to make a plot of the velocity as a function of time. But the velocity of a function of time is just dx dt. So I'll take the derivative of the expression I have up here, or time derivative of 15 minus t squared. Okay, and that's just negative 2t. Okay, so all I have to do now is figure out the velocity at these times. V of 0 equals 0. That's from the formula, but also we know she starts from rest. V at 1 second is just negative 2. These are all going to be meters per second. V of 2 seconds will be 4 meters per second, negative. V of 3 will be negative 6 meters per second. And finally, when she reaches the stage at 3.9 seconds, her velocity will be negative 7.8 meters per second. Now notice that all I need to plot here is a straight line. We knew that. This is the equation of a straight line here. So to simplify my life, you have a couple of choices how to make this plot. One would be to draw it like this. 1, 2, 3, 4 seconds. Have velocity here. Conventionally, positive is up. And I see that I have to have a maximum of negative 7.8. So I'll just make it negative 8 here. Negative 4 there. And realize it's going to be a straight line at 3.9 seconds, almost 4 down to here. And that'll be my plot. And these other data points should and do fit here. You could, if you liked, make a plot like this and and say that you're plotting negative v, and so say this is negative, -4, -8, and make it plus, or say you're plotting v and having negative go up. That would be okay too, as long as you clearly indicate these are negative velocities along there. Okay. Both are fine. So I'm done with problem number 1.